to talk about Qiskit, brief about the basics in Qiskit. So I am guessing most of you already have done this. But if you have any question, please let me know. You can open your mic or let the question in the chat. So as you already know, we need to install Qiskit, pip install Qiskit, and in order to start to working with quantum circuits, we need this class. And then the first step is to indicate how many qubits we want in that circuit, in that quantum circuit. In this case, we can say, in this example, we need or we want 3 qubits, right? So I know in the QBronze code, usually they start a quantum register first and a classical register, but actually it's not necessary since the class also receives just a number, and this number refers to the number of qubits. And if you send a second number, the second number is going to refer to the number of classical registers. So, for example, let's think in this state in which we have 3 qubits and has a 0, 0, 0 and 1, 1, 1 only. So to achieve this state, we can perform exactly these gates. First, a Hadamard gate to the first qubit. Remember in Qiskit, we have this order. So when I say apply Hadamard gate to the 0 qubit, I am referring to this one, so to the most to the right. All right, then we apply a control X, where the first parameter is the control and the second parameter is the qubit in which we are going to apply, in this case, the X gate. And a second control X or control not. So once we do these gates, we can visualize the circuit by using the draw method. The ordering is not messed up. The IBM decided to use this order because this has a similarity with the order on bits. When we are talking about classical state, we have this order, right? The most to the right is the less significant bit. That is why they decided to do this, because the similarity to the classical bits and that order. Well, you already know the draw method. This parameter is to indicate that we wanted to see as using matplotlib. So in order to execute this instruction, you need to install matplotlib also. So, well, here is the thing that I mentioned about the order. And the important thing, okay, you have your circuit, you have your gates that you apply to your circuit. Now it's important to simulate that circuit, right? So for that, we have several options. One of them is using the state vector. With this class, we can take our circuit and ask for the quantum state in Dirac notation. So when we use this class, we can apply it to our circuit that was called circ, and we can draw the state using LaTeX. And as you can see, this is the state that we wanted, as I mentioned before, this one. So let's note that square root of 2 over 2 is equals to 1 over square root of 2. So it's the same state. This is very useful because we can draw the actual representation, mathematical representation of the state, right? For that, we need this package that is quantum info. It is important to notice that it is in a different package. And also we can visualize the state as a vector. So for that, we can use this method, write to LaTeX, and send the state that we get here when we create the state vector. So in this case, we can see all the values in the vector that are represented in this Dirac mathematical notation, right? So these are two equivalent. This is also useful because it is common that we want to know how is our state in a mathematical form. Well, another visualization that Qiskit specific is this, called the Q sphere. This is only this is an IBM invention. This is useful in the sense that you can visualize the value of the phase. With these all colors, you know where is the phase. In this case, both are in blue, meaning that the phase or the number that is before this is the same, right? And is positive. There are other ways to visualize the state. This is called Hinton. Almost nobody use this type of visualization. But for example, this is important. We can print out the unitary that represents the circuit by using the operator class. So just by creating the operator class with the specific quantum circuit, we can have the matrix representation. So because you have a state and apply several quantum gates, your circuit has a matrix representation, right? That is the result of all the matrix vector multiplications that represents applying the quantum gates to one state. So in this way, we can have the matrix. It is also useful because it is common that we want to see how is our circuit going, right? So there are other kind of backends like this one. In what does this representation help? Somebody is asking, well, for example, when we were talking about the Grover search algorithm, in there is useful to see if we have the correct state marked. And in that sense, if you print out the unitary matrix representation, you can see which states have different phase. In the examples in QBronze, we are going to go through that. But in that examples, they usually have a minus. That is how we can see that the correct state is marked and the Grover search is going to work as we expect. Okay, here we have another quantum circuit with 3 qubits and 3 classical registers. As I mentioned before, we can send the quantity of both things in the construct of the quantum circuit class. When we apply a barrier, we are talking about this line, and this is only used to set some order in the circuit. It has no meaning, has no consequences regarding the quantum state. It's only to have some sense on which we are, step we are working on. So we can see that there is a separator, but only to visualization purposes. Then we apply measurement. With this syntax, we are saying we want to apply to the 3 qubits. This range is returning a list with 0, 1, and 2 indexes. Also this one. So we are saying to the first qubit, add a measure and save it to the first classical register. and so on for the second qubit at third qubit. And we show the circuit, right? Well, this is a way to say in which order we want to show the measurements. So next, we want to simulate the circuit. In this case, we want the statistics of running the circuit, right? So for that, we are using the R simulator. We create the simulator, and not always is needed, but it's a good practice to perform a transpilation before. And the transpilation has to be done specific to the simulator. So that's why here we specify the quantum circuit and also the simulator, in this case, the air simulator. So in this way, we are saying that the quantum circuit is going to work specifically for this simulator. Once it's transpiled, we can run the simulation. We specify how many times we want this execution to be done. In this case, this number, actually this number is the default value, but here we can specify any number we want. If we do this, the quantum circuit is going to perform only once, but we usually want several times in order to create that statistics. So once we have the results, the run is finished, and job sim, we have the results. And with that, we can obtain the counts. And we can see that the specific circuit that had these two states, after running 1,000 times, we are getting almost half of the time one of the two possible states, and almost the other half time the other state that is possible for this quantum circuit, right? This notebook is part of the Qiski documentation. Let me show you. If you do Qiski documentation, tutorials, this notebook is specifically this one. So another visualization, as you already surely see, is the histogram, right? In this way, we can see this information, but more visually. We can see that we have almost half the time each of the states. This is the very basic stuff of Qiski, sorry. And when you can always check the version of Qiski you are running by using this. The current version of Qiski is 43, but the Qiski is constantly upgrading its code, so this may change over few months or less than that. So, well, I am supposing you already have done some of this stuff. I think the new things are these ways to visualize the state, which I think is really useful. So let's see a little further about Qiskit. Let's talk about the operations that we can do. All right, as you already know, this is a general representation of a quantum state of one qubit. Also can be written like this, and this is the block sphere representation. And in general, when we want to evolve the state, we apply a unitary We call these matrices unitary because all the quantum gates are unitary matrices, because we want them to preserve the length of the quantum state, right? Because that length represents the probability, so we always want the probability to be 1. So, for example, general unitary could be this, but the most general one in quantum computing, a quantum gate, is called U, just U, and is represented by this matrix. And takes 3 arguments that are using like that. Actually, all other quantum gates has an equivalent with this U. All other 1-qubit quantum gates. So Qiskit has implemented this U, that is the most general unitary gate. So if we use quantum circuit .u and send the 3 parameters, we can use it. The last parameter corresponds to the qubit to which we want to apply the U gate. In this case, Q is a quantum register, so just one quantum register, that's why this is the last parameter. We can draw, as you can see, if we don't send the parameter MPL, the drawing is in text, in plain text. But if we use the MPL, we have this. Oh, so sorry. This. So we can execute this simple circuit that has only one gate, and for there get the unitary representation of that circuit, because the backend, I didn't mention it, is the unitary simulator, similar to the previous one. So that's why we get the unitary matrix that represents the whole circuit. So here are some equivalences. The U gate is the one that exists now. If you check out, for example, the documentation of Quasum or other places, you can find that exist other gates called U1, U2, U3, and these are the equivalences in the U gate. But regarding to Qiskit, these gates have been deprecated. So if you want to implement them, you have to use the U gate. So the phase gate. This gate is in charge of adding a phase to our state. It's equivalent to this matrix, and you only need to do .p to the quantum circuit. Specify the value of the phase and the qubit to which you want to apply the gate. In here, we are also getting the unitary. The identity gate, as you may know, it does nothing because it's identity. So in order to use it, we do .id for identity. The public gate is .x for the bit flip gate. Here is the equivalence in the generic U gate. The Y gate performs a bit and a phase flip. This is the equivalence in U gate, and it's only to do .y. I don't understand what you're saying, David. It is QBronze notebook sets. The set gate is the phase flip. It's equivalent to the phase gate, but with specifically a phase equals to pi. and it's this, right? Also, the face gate has an equivalence in U gate like this. This is the Hadamard gate. To use it, we only need to do .h. And this is the equivalence in U gate. The S gate is the square root of set, right? And we can use it with .s only. So depending on the algorithm, you are going to need all these different gates. The important thing here is to know which ones we can access with Qiskit in a direct form. I mean, using the variable of the quantum circuit dot the name of the gate, because not all the possible gates are implemented directly. But these ones, they are here. And this is the conjugate of S, which means is the same one. We add a phase of P over 2, but the conjugate adds a phase of minus P over 2. And in this case is called SDG. We also have a T gate, which is the square root of S. So when we apply set gate, let's notice this, the phase is equals to pi. When we apply S gate, the phase is equals to P over 2. And we apply the T gate, the phase is equals to P over 4. And also have the conjugate version for T. It is going to be TDG, which means the phase is negative. And in general, we can have any rotation. For example, the X gate is a rotation with a value of pi. But if we want any amount of rotating around X axis, we can do it, but using the Rx. In this case, we are asking to rotate around X axis about P over 2. In this point, I am talking about in the block sphere. Because when we are talking about in the unit circle, the rotations that we can make are only around the Y gate, right? Actually, that was an exercise in the quizzes, I think. So please note that rotations about any of the three axes is because we are already in 3 dimensions in the block sphere. And for that, we need to work with complex valued qubits. But regarding QBronze, we are working only with real valued qubits. So that's why we can only use RY. So, well, this is the corresponding rotation around Z axis. And we can also have multi-qubit gates. For example, the control ones, right? For that, we perform the Kronecker product. In that way, we can have, if A can be a 1-qubit gate, B is a 1-qubit gate, and when we take the Kronecker product, we are going to have a matrix that is twice the size in order to be able to apply that new gate to a 2-qubit system. Okay, so we have the control versions of the qubit of the gates. Sorry. For example, this one is the control X gate, in which we say the first parameter is going to be the control, represented by a dot, and the second parameter is going to be the target. And here we represent it with the actual gate we want to apply if the control is equals to 1. In this case, it's an X. That's why we have an X here. We have the control Y version also and the control Z version of the gates. This is the same representation, but here is kind of a weird representation about the control Z gate. So in this case, since we are only applying a phase between these two qubits, that's why the representation is this, because it really doesn't matter where is the phase actually. The important thing is the phase is a difference in the phase between the two qubits. So please don't be afraid of this representation. It's the same, it's the control set. We can also apply the Hadamard in a control way, which is going to be the same logic. We also have control rotations. In order to access that, we only need to precede the name with a C. In this case, we have the amount of rotation we want to perform, the control as second parameter, and the target as third parameter. So this is the representation. And it's going to be the same. This is, for example, the control phase rotation. We know that phase gate, it was represented with P, and the control version is CP. And the general gate, which is U, also has its control version, which is going to be CU. We send the three parameters, theta, phi, and lambda, and also the control and the target. So swap gate. The swap gate is not a control gate, but it is a 2-qubit gate. The swap gate, what it means is that we want to swap the two qubits. So for example, if we start with 0, 1, we are going to end up with 1, 0, and so on. So in this case, it's the same thing if we say this or if we say this, because we are only swapping the qubits, right? So these two lines are equivalent. And the representation, please note the difference. These are X's or crosses, right? It is similar to this representation, but actually, this is not a dot. This is a cross, right? So for example, if you use NPL, we had an error, I don't know why. Okay, well, I need to run everything. So 3-qubit gate. In this case, it's going to be applied to 3 gates. For example, the Toffoli means that we have 2 controls, and the third parameter is going to be flipped or not, depending on the controls. If the controls both are 1, then the X is going to be applied to the target. The Toffoli gate is going to be accessed with CCX. And we specify control, second control, and target. So both controls are represented with dots. We can also have a control swap gate. In this case, we are having a 3-qubit gate, right? So the control is going to say if we are going to apply the swap gate or not. If the control is equals to 1, then we are going to swap these 2 qubits. these two, the last two parameters. This is also called Friedkin gate. And we also have operations that are not quantum gates, are non-unitary. So for example, the measurement, for that we specify the measure over the quantum circuit and say which qubit is going to be measured and in which quantum register, classical register is going to be stored the result of the measurement. All right. Another operation that is not a quantum gate is the reset. With this, we can reset the state of a qubit into the zero state. Because all the qubits start in zero state, we apply some quantum gates, but for some reason and some moment, we want to reset one qubit to the zero state. But let's note this is irreversible. And in Qiskit, we also have, well, this is kind of old. We have conditionals to apply operations. So, for example, this line is saying that the X gate is going to be applied to the zero qubit, not to the qubit at the position 0, if the classical value stored in C is equals to 0. But this is, as I mentioned, quite old. There is a new way of doing this. And this is going to be, actually, this is deprecated and is going to be removed in a few next months. And also we can do the initialization we want. So we define a vector because we want to start the state of a quantum circuit with a specific vector that represents the state of the system. In this case, our phi state defines a 3-qubit system. And these are the values we want to start with. So for that, we create a list in Python with the values that we want. So because we have 3 qubits, we are going to need 8 values, right? N equals to 3 because there are 3 qubits, and 2 to the n is equal to 8. That's why we need 8 values. So these values correspond to dimensions here. And we can do quantum circuit dot initialize and send the vector that represents the state we want to start with. And the second parameter is are the qubits to which we want to apply the state. Because actually this circuit could be maybe 8, but this state is going to be only in the first 3 qubits. Okay, you can see more details in the corresponding notebook. This is also a notebook from the Qiskit documentation. So now I want to talk about a specific example in QBronze. That is the Grover search implementation. So how do we use Qiskit to do this Grover search? Okay, so I hope you already read this, or you have an explanation about it. So for example, this task is asking us to implement the query phase and check the unitary matrix for the query operator. So when we have n equals to 4, big N is because we want 4 states, right? And how we do get 4 states, well, we need 2 qubits, right? Because 2 to the 2 is going to be equals to 4. So for having 4 states, we need 2 qubits. And well, it's also mentioning that the function f that corresponds to the quantum operator is already defined here in this file. So let's see. We are going to need an auxiliary qubit. So I mentioned that we need 2 qubits to represent the 4 states and plus 1 qubit to have the auxiliary one. With that, we create the circuit. We initialize the ancilla as mentioned in the explanation. For that, we are going to take the last qubit, in this case is in the index 2, apply X and H. It's part of the Grover's algorithm. After that, we are going to apply the operator UF that is defined here. And then we need to set back the ancilla by applying the same gates, but in an inverse order. So apply H and X to the ancilla qubit that we decided is going to be the last one. So that's why we specify the index 2. And then we get the unitary. And when we print out the unitary, we can see that the UF operator is marking the state 1-1. Okay, this is what this operator is doing. It's going to mark in some way the state 1-1. And this is going to in order to mark the state is adding a phase of -1. Okay, so with this code, what we have is that we are marking this state. So we can then perform the Grover search, and the Grover search is going to find this because this one is the one that is marked. And also here is the circuit. We can see the gates that we apply explicitly in here. First X, then H, after UF, H, and X again. So this is this line, right? We can see that inside UF, the thing that is doing is applying a Toffoli gate, right? Taking the first 2 qubits as controls and storing the result in the 3rd qubit. In this case, it's going to apply an X gate to the last qubit. So this is everything that this line is doing. And as we saw previously, this is the resulting matrix. So let's talk about the inversion operator. The inversion or diffusion operation needs these steps. So these steps is telling us what we want to perform in our code. So for example, again, let's take n equals to 4. And it's asking us to implement the inversion operator. And review that we are obtaining this matrix. So the inversion operator, because I imagine you already studied this, is going to be like this. Step 1, as mentioned over here. Set the ancilla to no, but we are talking about this. Apply H to all qubits. So in here we are receiving the circuit and the qubits that are the qubits that represent the system, but this doesn't include the ancilla. So first step is to apply H. Here we are assuming that we have only 2 qubits. That's why it's hard-coded the quantum register 0 and 1. Step 2 is apply X gate, right? X to all qubits. Then apply multi-control NOT operator, where all the qubits are the controls and the ancilla is the target. So this is it. This is the Toffoli gate or double control X. These two are the controls, and this is the target. And then we need to apply X again to all the qubits, as mentioned here. Then we need to apply X to the ancilla qubit. In this case, we apply X to all of them. And after that, the H. And that's it for the inversion algorithm part. So let's see if this is doing what we want, right? So we are going to do the same as in the previous exercise. We are going to prepare the ancilla, then call the inversion, the method that we just created here, and set the ancilla back to the original state by applying the same gates but in an inverse order. So we execute this in the unitary simulator in order to get the unitary, and with that we can confirm that the resulting matrix is the one that we expected. And this is the circuit. These are all the gates that we apply inside inversion, and these two, right? So these two are part of this. Then the inversion includes all of this. And this is part of the inversion, and this is getting back the ancilla to its original, right? Hope this makes sense. So here, what we need to do here. Okay, here we are going to perform the whole Grover algorithm. So for that, we have 3 quantum registers because 2 are corresponding to the system and 1 is an ancilla. And here we have 2 classical in which we want to store the values of the 2 qubits that represents the system. The first step is to generate an equal superposition by applying an H to every qubit. Then prepare the ancilla. At the end, we are going to set back the ancilla, but in the middle, we want to perform the Grover's iteration. So Grover has 2 main steps, the query and the inversion. Right? With the query, we are performing the operation of marked the element we want to find. And with the inversion, we are going to invert, how do you say, to really marked the element. I don't know if you remember this. Sorry, this process, right? This is the inversion. We start with equal superposition. This we mark it, and this we perform the inversion, which means we have the one that we wanted, but with more probability, let's say. So when we execute the circuit, we are going to find this one, right? So this is the inversion process here. And after that, we are going to measure the qubits that belongs to the system. In this case, qubit 0 and 1, and perform the simulation, right? So this is the full circuit. This is the preparation. We set an equal superposition, the 2 qubits of the system. This is the preparation of the ancilla qubit. This is the query part of the Grovers. And this is the inversion part of the Grovers. And this is in this part, we set back the ancilla. And we perform the measurements of the 2 qubits of the system and store that measures in the classical registers. Okay, so in this case, we are doing this only once. Well, we can perform these query and inversion steps many times as needed. So because this is a very simple example, with one iteration is enough to find the state we want to find. But in more complex and more big examples, we need more iterations. So for example, this one. If we have upper n equals to 8, so we need 3 qubits. And also we need 2 ancillas. That's why we are using 5 qubits. So here are the instructions, and this is the result we want to achieve. For that, the inversion method that we had before is not going to work because this method is prepared only for 2 qubits. But now we want some inversion for 3 qubits, right? So this is the corresponding version of the code for a system with 3 qubits. It's the same, just in this case we are having some force in order to write less lines of code, but it's exactly the same logic. And also when applying the Grover's logic, it's also the same. In this case, we are only applying the inversion and watching what is the corresponding unitary matrix. And yes, we are getting the matrix that they ask us. But it's the same logic. So for this example, it's also the same thing. In this case, we have the UF8 function provided. So we only need to prepare the ancilla, prepare the equal superposition for the 3 qubits. As I mentioned before, the barrier is only to get some order in our circuit, but it means nothing to the execution. And we apply the query, which is defined inside this function. And then applying the big inversion that we saw before. And in this case, we are doing this twice, because the circuit is bigger. So one iteration is not going to be enough. And finally, set back the ancilla. And now, well, we want to measure in order to confirm that we are getting what we wanted. So if we see this, we can see that the state that is found is the state 011. So the query inside this function, UF8, is actually marking the state 011. And in the drawing of the circuit, we can see that this is the preparation step. This is the query. This is the inversion. This is the query and then the inversion because we apply it twice, right? And finally, we set back the ancilla and measure the 3 qubits of the system. So an important thing is to design the oracle, to define the way we can implement the query. So for example, if we want to mark the state 11, what we need to do is applying a Toffoli with the two states, with the 2 qubits, 2 first qubits, and the third one is the ancilla. So in the ancilla is where we are going to store if the state is equals to 11. So here we are going to apply the X gate. Okay, so we perform the whole algorithm. Prepare ancilla, apply the oracle, and put back the ancilla. So with that, in this case, we are only testing the oracle or the query. So as we can see, the marked element is the 11. So let's remember this, we have the 00 state. This represents the 01 state, 10 state, and this is the 11 state. Same in this, in the rows. So this is the value of the 11 state, and this is the one that has the phase change. So this is in this way we can see that the 11 state is the one that was marked by this oracle. So the circuit of this is this corresponding. This is the preparation on the ancilla and set back the ancilla, but here this is the oracle. In this case, it's only a Toffoli gate. But with this, what is happening here? Well, if this qubit is 1 and this is also 1, so this gate is going to, these controls are going to perform the X gate to this one, right? Because the state here is 1 and the state here is 1. But if any of these two states is 0, this is not going to turn on, and the X gate is not going to be performed to the ancilla. That's why the oracle is like this. So, but what happened if what I want to mark is the 01 state. So we are going to use the Toffoli again, but because I want the first qubit to be equals to 0, so I am going to apply an X to that qubit. So if I apply an X to this qubit, and that value comes with a 0, let's see the circuit like this. So I want 0, 1, but this Toffoli gate is going to be turned on only if the two qubits are equal to 1, right? So because I want this to be 0, I flip it. So now it's going to be equal to 1. And this is 1. So now this gate is going to be applied because the both values are equal to 1. And after that, I reset, I restore the value of this second qubit because it started in 0 and I want it in 0. So when we apply the measurements over here, it has its original value. So in order to mark the 0, 1 state, I need to flip the value of the 0 to 1 so I can apply the Toffoli gate. Hope that makes sense. Now, if the oracle wants to mark the 0, 0 state, so I need to apply a flip gate or X gate to both qubits. Right, to the 0 qubit and 1. So I have this. In this point, if this is 0, I flip it, and here I'm going to have a 1 state. Also the same thing here. This is 0, after X, this is 1. So this Toffoli gate is going to be turned on. And I am detecting the 0, 0 state. And after that, I turn them back because originally it was equals to 0. So after this, here I have 0. Also, I have here 0. And that's it. In this way, I mark the 0, 0 state. And as you can see, after the execution of the circuit, we can see that 0, 0 state is the one that was found. All the time was measured the 0, 0 state, because this part, the query or the oracle, is marking the 0, 0 state. So this is the preparation, this is the query, this is the inversion, and this is the final step, that is the measurements. So a more complex example is this, in which is asking to mark the 001, a system of 3 qubits, and also the 111 state. So in order to mark the 001, we need to flip the zeros. So we apply the X gate to those ones. And at the end, we are going to send them back to the original state. But in here, we want to apply a triple control X gate. Right? So in order to have that, if we wanted to apply a double control, we were using this, right? But this does not exist. So the function that we can use in the circuit is called MCT. MCT takes as many controls as you want and apply an X gate to the target value. So here we have two parameters. The second parameter is the target. But the first parameter is a list of all the controls I want. In this case, I want 3 controls because I have 3 qubits in the system, right? So I have these 3 controls inside a list. And the second parameter is the target. So with this method from quantum circuit called MCT, I can do that. If the circuit is bigger, I can add more controls here, as many as I want. So this is very useful method, right? And after that, I also want to mark the state 111. And for that, because all are already ones, I only need to apply the MCT, the triple control X gate. I don't need to change, I don't need to flip any qubit because all of them that I want to find is equal to 1. So here we perform Grover, same steps. Here we are showing only 1 iteration. And as we can see at the end, the after the execution, the correct states were found, 001 and 111, right? Because these ones are the ones that we marked with this oracle. So here's the initialization. This is the oracle. This part corresponds to marking the 001 state. And this part corresponds to marking 111 state. This is the inversion. And this is the measurement, the last step. In this case, I am using the big inversion because this one is for 3 qubits. This is a method that we saw previously. So, well, in this example, it was enough to execute this only one iteration, right? It was enough and found the states we wanted, the states that we marked inside the oracle. So that was that's it. I'm sorry, I passed by 6 minutes. If you have any question, please let me know. The notebooks, okay. This notebook, this right now is from the QBronze material. So it's Grover search implementation. When you start QBronze, you can access that notebook. Is this one, the last one. Okay, you can find the QBronze material in the GitLab. This is it. Here you can download directly with this button. You can download as a zip. And the other notebooks that we watch now are in the Qiskit documentation. So for example, the first one is this, and you can click this link that is going to send us to the Qiskit GitHub. And here you can also do downloads. And the IPYNB file is going to be downloaded as the same as this. It's exactly the same as I run. And also the second notebook. Oh, what was it? Summarize of quantum operations. Is this one. Also, the corresponding link is here. And well, if you want to go deeper, well, there are a lot of tutorials about Qiskit in this page. You can download all of them and run it locally. Also, you can run these notebooks from the IBM Quantum Experience directly. Sessions like this one, as you mean, MK? I don't know. I don't know, but you can ask for them. I am giving this one because I have the understanding that some people were asking about to have a session like this in which we can talk about more deeper about Qiskit. So maybe you can ask for this regarding QNicken in order to review specific things inside QNicken. And then I guess the organizers of WOMANIUM can give that options. And of course, if you have more questions, you can drop them in the Discord server. We're trying to be aware of that. Also, other people very nicely also answer questions. So let's build a community. And well, if there is no more questions, I think this is it for today. Thank you so much for being here.